Priya, can you hear me? Bas, that's it. We start. Now, so yesterday we had finished with what you call the general properties, in which we had discussed the last was what? It was the reactivity towards halogen. It's clear. So today we are talking about the anomalous behavior of oxygen. I told you, normally in the board what happens is, they ask a question, anomalous behavior of nitrogen, anomalous behavior of oxygen. Much more important is anomalous behavior of fluorine in the next chapter. Very, very important. Look, there, every question is a MCQ. Is it clear? So today we are dealing with what? Today we are dealing with anomalous behavior of oxygen. See, I told you, even in the, if they ask a short note on the anomalous, so there are two types of questions they can ask. Give scientific reason, complete, discuss anomalous behavior of oxygen. It could be a 3-mark question, 6 points. And there, when they ask such a question for 3 marks, actually there is not many points that you can write. So what they do is they allot a certain amount of mark for why it shows anomalous behavior. So that introduction part is, so every time anomalous behavior of nitrogen, anomalous behavior of oxygen, next we're going to study anomalous behavior of fluorine. Why they show an anomalous behavior is something which you should always write. So why does it show anomalous behavior? It shows anomalous behavior obviously because of what? First is, it shows anomalous behavior because it's due to anomalous behavior is due to. So this introduction, why, is very, very important. First and foremost, our standard point, it is a small size or small atomic size. We have small atomic size. Okay, the second one that we have is very high electronegativity. I told you that most electronegative element is fluorine 4 on the Pauling scale, and then we have oxygen, which is 3.5. Then you have chlorine 3. Then that way. So highly electronegative. Highly electronegative. Highly electronegative. And more important is absence of vacant D subshell. So, like it cannot extend its valency or oxidation state to a higher oxidation state. It gets limited to a certain oxidation state. That's because of absence of vacant D subshell. Absence of vacant D subshell. So what are the anomalous behavior? First, here there are only 2 points. I may discuss all the points, but from the exam point of view, there are only 2 points that we have to remember. What is the first thing that we have? You have oxygen, sulfur, selenium, tellurium, polonium. So I'll just write it down: oxygen, sulfur, selenium, tellurium, polonium. So reference becomes easy. So oxygen is a gas. All other fellows are solid. Okay, all are solid. So here this is the first anomalous behavior, that oxygen is a gas. Oxygen is a gas, whereas I don't think they'll ask such a foolish simple question, which is not a solid in this case, because everybody can tell oxygen is a gas. Okay, at least they are not that demented now to ask. Is it clear? So this would not, there would not be a question like that. Okay, so whereas other members are solid. Okay, this is a point we have to write, but then that's for the board exam. Oxygen is diatomic. Oxygen is diatomic. So we have O2. Oxygen is diatomic. So dioxygen. That's why I told you. When I say oxygen, I am saying dioxygen. Because I told nowadays this problem has arisen that You have to say it's dioxygen. Oxygen means oxygen atom. Okay, so it is diatomic. And what happens? Main thing, while others are polyatomic, while others are, of course, not polonium, while others are polyatomic. I told you, if you remember, sulfur was S8 and selenium is also S8. They are octa-atomic molecule and they have, remember this word, puckered ring structure. One for sulfur, bond angle was 107, bond length was 104 picometers. So these values you remember by heart, structure and A, because one question in the board they ask is give a structure also. So sulfur octaatomic says puckered ring structure. It is puckered ring structure. Then we have the third one. That may be important because molecular oxygen that is O2. We have done this in the 11th standard in Nature of Chemical Bond. In fact, the whole molecular orbital theory had to be considered because oxygen, the valence bond theory could not explain the diatomic nature of oxygen. That's why we had molecular orbital theory where we said that oxygen is paramagnetic because it has two unpaired electrons in the sigma star 2px and sigma star 2py anti-bonding orbital. Remember that. So that itself is an MCQ on its own. So molecular oxygen, I'm just revising in case you have forgotten. So oxygen is paramagnetic. Molecular oxygen is paramagnetic. Whereas others are, that can be a question which can be asked. Is it clear? I'll tell you how they'll trick you. So molecular oxygen is paramagnetic, whereas others are diamagnetic. Others are diamagnetic. See, when we talk of sulfur, the normal sulfur that we talk about is S8. But remember one thing, but S2, sulfur diatomic molecule. What we are talking is diamagnetic is this fellow, S8. It is diamagnetic. But S2, diatomic sulfur, is paramagnetic. Like O2. So this can be a question on its own. Which is paramagnetic, S2, S8, then Se8, something like that they can always add. You might miss the point because we are saying everything is diamagnetic. Sulfur, octa-atomic molecule is diamagnetic, sulfur diatomic is paramagnetic. Remember that. Then what happens is, fourth one, oxygen exhibits an oxidation state of -2. Oxygen exhibits an oxidation state of -2. It is clear, -2. Okay. Then you have peroxide -1 and all that, but it cannot exhibit higher oxidation state. Like sulfur hexafluoride. We had sulfur with charge +6. Not charge, sorry, oxidation state +6. It does not exhibit higher oxidation state. Why? Due to absence of vacant D subshell. Due to absence of vacant D subshell. Is this clear? Hydrides of, what do you call that? Fifth, hydrogen compounds of oxygen. Means where hydrogen is attached to oxygen. Hydrogen compound of oxygen show hydrogen bonding. Show hydrogen bonding. Nothing more in that. Okay, I told you, except for two. Then hydrides of oxygen is liquid. Hydride of oxygen, that is our friendly neighborhood water. It is clear. Yeah. Is liquid. This is definitely a point to be A. Whereas others are, whereas hydrides of other, whereas hydrides of other elements of the group are gases. So this is, I told you, the kind of question. Only two are important from the entrance exam point of view. Please take down this much, and then we will come to dioxygen preparation, occurrence, preparation, and chemical properties. That much we should complete today.
So,
Ah,
so all the group 16 elements are paramagnetic except for oxygen and sulfur.
what are you saying?
So all the group 16 elements are diamagnetic except for oxygen and sulfur.
Sulfur also S2, not S8. Be careful about what I'm saying.
Yes, sir.
You understand? S8 is diamagnetic, but there is sulfur diatomic also available, but that would be paramagnetic like O2. So I'm very clear about what I'm saying. But S2, sulfur diatomic, is paramagnetic. When we are talking about others are diamagnetic, normal one. In the normal, sulfur occurs as S8, selenium occurs as S8 and all that. They will be diamagnetic. But if it is S2, diatomic sulfur, that will be paramagnetic. You got it, Priya, what I'm saying?
Yes, sir.
You can look at past question. This has been asked, which is paramagnetic, and they have given S2. And that you would not know that S2 does exist. I mean, they may exist at a higher temperature, all that story apart. But if S2 exists, that will be paramagnetic. Okay. Now we start with dioxygen. I told you, when we say oxygen, nowadays they're considering to be atom. So when we have to talk about O2, we have to talk about in the molecular form dioxygen. So our usual, how does it occur, how much percentage, what all that, those are factual questions. Generally, that factual questions are asked in the Maharashtra entrance exam, okay, MHCET. So what we have is, we are now talking about dioxygen. When you talk of dioxygen, what happens? Abundant, it is an abundant element, all that occurs is correct. So in the occurrence, when we talk of occurrence, what happens? It is 21% by volume, 21% by volume of air, of atmospheric air. 21% by volume. So this can be, I think, I don't know. But 50% of Earth's crust. I think this is something which most of you have been indoctrinated since 7th standard. Okay. But maybe the second one you don't know, that's continuing. Of all the minerals ores that is present, 50% of it is made up by oxygen. So that is a very important point. Okay. 50% by weight. Let us be very clear. 50% by weight of Earth's crust. 50% by weight of Earth's crust is E. Then what happens is, it is a product of photosynthesis. Is this clear? It is a product of, it is released in air as a product of photosynthesis. So what are the methods of preparation? We straight away come to methods of preparation. When you talk of methods of preparation, I told you, sometimes we don't realize these. I have got some very deadly applications. I told what are the. I mean, today, Pakistan is a failing country. It's karma. They deserve it. But you know what they were doing actually? I mean, even in 1993 bomb blast, they picked up some 15 fellows from here in Bombay, took them to Pakistan and trained them for bomb making. What is the training they are giving? They are giving training of chemistry. What are they doing? They are trying to explain to them what are the simple different chemicals that are available in the local market. Then what are the names? What is it? What is the precaution? And then they say, okay, how do you assemble that? You see, put it in a cooker, and then they have to assemble a timer and then blast it. It's clear. So this must be a 1 or 2 months training that they are giving. I mean, these are illiterate people they are giving. If they were to take some literate fellows from here, then they would have had bigger problem. There used to be a fellow, I mean, he was popularly called as Tunda. I think he's arrested and brought back to India. He was arrested in Kenya. Now, Tunda in actually, I think Punjabi means somebody who doesn't have a hand. Tunda. So he was, one of the days when he was making a bomb, what happened was the bomb burst in his hand and he lost his hand. That's why it's called Tunda. And that was a master, what he called, trainer of how to make bomb. No chemistry language, this thing. We are all fools to do MSc and all that. He was training otherwise also. So the application is over here. I mean, where does it start? So anything to burn, anything to burst, you need two main gases. One is some chemical which will decompose on heating to give nitrogen. Okay, so now if you're closing it somewhere in a closed vessel, for that burning to happen, you need oxygen, because combustion is requirement of oxygen. You understood? So therefore, this what we are talking general method. Use some chemical, heat it, and oxygen will be generated. It's a very common chemical sometimes. It is clear. So this is what they are teaching. That look, you have to use some chemical which will generate nitrogen. What was it? If you remember, I told you nitrogen, ammonium nitrate. It is available in plenty. Fertilizer. So anybody buys a sack of fertilizer, people think he's a farmer. But then the ulterior use could be this. But that alone is not going to help. You need something else to, if that burns, that gives nitrogen. But for it to burn, you need to have oxygen. Na? That's where this part comes, Okay. Don't think I'm trying to train you to do something like that. Please don't. It's dangerous. It's clear your life will become hell. You'll get badly thrashed by the cops. Badly. I mean, you can imagine what will happen. We are peace-loving people. But we should know when they say continuously, these fellows had trained all our terrorists. They had taught them how to make bomb. That means they were expert chemist fellows sitting there and training them. Is it clear? I mean, you can imagine they had the knack of doing printing fake notes. That's also chemistry, exact composition of the dye and all has to be made. It is very precise chemistry actually. This is knowledge being put to bad use. Is it clear? So we are going to put it to good use. We are going to get marks and we go ahead in life. Swayam samjha kya? Swayam, Priya, and all the people who are listening to the live stream. We had something different in life. But what happens? See, look at this. Potassium permanganate. Any pharmacy shop, you will get potassium permanganate. Half a kilo, aram se mil jayega. You'll be too happy that somebody is buying half a kilo. Because why would a normal man buy potassium permanganate? I had told you. You have vegetables, especially the vegetables which are rooted vegetables, like carrot, season hai, radish, season hai. You should scrape it and put it for 3 minutes in a solution of potassium permanganate. Why? Because these rooted vegetables have ascaris, worm. So if you boil it, it still won't die because it has got those eggs which have got wax coating. Potassium permanganate is oxidizing the wax and then killing the ascaris, this thing. the seed, I don't know biology what they call it. I'm not getting the name. So ascaris will die otherwise. Even its seed, this its egg, has got a coating. This is clear. Dangerous, because ascaris from your stomach can go into your brain through your blood and cause epileptic fit. So that these problems are there. So that's why we are supposed to wash all vegetables, especially the rooted ones like carrot, radish and all, with 3 minutes you put in potassium permanganate. Okay? So potassium permanganate is sold for that noble purpose, to protect your health. But what these fellows can do, they can combine potassium permanganate, heat it. They can combine it with what? Ammonium nitrate. Correct? And they'll put lube oil. So lube oil will burn first with little oxygen. That will generate heat. And what will happen to potassium permanganate? It will decompose immediately. It will do its job. It will form K2MnO4 plus MnO2 plus O2. So oxygen. More burning will take place. That heat will decompose ammonium nitrate. It will generate nitrogen gas. Nitrogen gas will expand. No scope for expanding in the pressure cooker. It is a blast. You understood? So next is what? You can have potassium dichromate, K2Cr2O7, widely available. Leather industry. They use potassium dichromate in huge quantity for tanning. And something which is non-suspicious, you can always get from some leather tanner, buy for me here, give me one sack full of this, I want to make some bomb. You'll get it, potassium dichromate. Heat it. When you heat it, what happens? You get potassium K2O plus 2Cr2O3 plus 3O2. Okay. You have potassium chlorate, KClO4, simply heated. This is more preferred. Compared to these two, this is more preferred. They are always looking for potassium chlorate. So that forms KCl plus what? Plus oxygen. So this is one method. Is this clear? I'll come to an interesting method and discuss a thermodynamic property. Now, the other method is, so this is the first type of method. Just general salts you heat. Then decomposition of metallic oxide. Decomposition of metallic oxide. Simply, you have mercuric oxide. Just heat it. It should be greater than 500 Kelvin. Any temperature above 500 Kelvin, they have said how much? Around 720. So around that only, 223 means above 500 Kelvin. That's very important. Less than 500 Kelvin, this reaction will not take place. I'm going to teach you why. What will happen? This will form mercury plus oxygen. Then you have got Ag2O. You should also have lead oxide. This is also around greater than, say, greater than about, we'll put as 620 Kelvin is about greater than 400 Kelvin. What will you get? You will get Ag plus O2. So what is this temperature got to do with it? Now, if you remember in thermodynamics, there's a foot ruler. Can you see the foot ruler? Either. Okay. Yeah. See, if you remember, we had taught you in thermodynamics that when delta G is negative for any reaction, what happens? The reaction is spontaneous. What do you mean by the word spontaneous? It happens on its own. Now, I told you, just heating mercuric oxide at what? At a temperature greater than 500, the reaction is spontaneous. Now, why is it spontaneous? This was studied. These kind of reactions were studied by a person called as Lingam. And so we have an Lingam diagram for oxide first. So what did Lingam do? It is clear. This is called that spelling, Canizuros, Lingam, these spellings have been always, what you call, little difficult. I make a mistake. So Ellingh, Llingham, Elllingham, Llingham diagram. So what did he do? He drew a graph of, listen carefully, he drew a graph of standard free energy change versus, let us say, temperature. Versus temperature in Kelvin. You can have temperature. Old books will show temperature in degrees centigrade. Doesn't matter. At 273 story वही होता है. It is clear. So what he realized is, suppose we talk about, I mean, this was 0.0 kilojoule per mole. Free energy change was, unit was kilojoule per mole. So here you had, say, I'll just write down the values so that I don't make a mistake. So this was minus 200, this was minus 400, this was not, it's not up to scale, huh? This was minus 800, and this was about minus 1200. So this will be plus 200. It is plus 200. So what happens is, when you start from here, okay, as you are increasing the temperature, the free energy starting. So what is the reaction we are talking about? This is 500 Kelvin, 1000 Kelvin, 1500 Kelvin, so on and so forth. So you see, we are tracking. He found a graph. He found a graph for formation of oxide for everything he drew. So you have, what is the reaction we are talking? Hg plus O2 forms HgO. So it started something like this. Okay. So in the forward reaction, okay, this is, I'll make it a little sharper. Huh? So around, it should be much sharper because 500 Kelvin we are saying. Right? So you can see Hg plus O2 at a temperature less than 500 Kelvin, delta G is negative. It is negative. Okay. Delta G is negative. But greater than 500, delta G free energy change is positive. So you'll say, sir, beyond that reaction will not take place. But imagine the reverse of the reaction, Laplace-Lavoisier law. Above 500 Kelvin, the reverse reaction HgO forms Hg plus O2. Standard free energy change is negative. So that becomes spontaneous. So if you want to form HgO, mercuric oxide, you have to keep a temperature around 200 degrees. If you say, no, sir, I will increase the temperature, you only taught me rate of reaction increases with increase in what you call temperature. That story is different. That was in chemical kinetics. Here I'm telling you a different story. I'm putting the thermodynamics part of it. In certain reactions, what happens? If you go by that logic, you will increase the temperature. In fact, the product form will get decomposed again. You're going nowhere. It is clear. So the reverse day. So why, when you have mercuric oxide, as long as the temperature is around 250, you are very happy. It is not going to decompose. But the moment you start heating more than that, when you come to 500, it decomposes. Or if you have mercury and oxygen, you're heating. It's getting formed. You're very happy. Temperature increases. 200, 250, rate of reaction increases. Sir, yeah, it is getting formed. Yes, you reach 500. But at 500, the whole story changes. At 500, the free energy change for the reverse reaction is negative, spontaneous. It starts decomposing. So that is why same story is for what? The same story will be for Ag2O. So Ag plus O2 forms, I'll put it like this. We had a blue pen, correct? So we can use that sometime. So here you have, you can see, it is much sharper. Okay. So this is Ag plus O2 forms Ag2O. Okay. Now, Up to around 250 degrees centigrade, you heat silver with oxygen, strong heating, it will become. But moment you cross that 400 around threshold, what happens? Your free energy change becomes positive. Reaction is no longer spontaneous. But for the reverse reaction, the free energy change becomes negative. It starts decomposing. So that is why temperature is a criteria. You cannot just have any temperature and go by that old natural logic. Increase the temperature, rate will increase. Increase the temperature, in this case, decomposition will take place. You will get back reactants again. So this is a Lingam diagram. Of course, a Lingam diagram was used for actually why carbon and carbon monoxide is used as a reducing agent. But this is an application here in group 16. Why certain metallic oxides, when you heat, okay, they just decompose to form oxygen. Like iron oxide does not, Fe2O3, okay, it does not decompose, but mercury oxide decomposes because at that temperature and beyond that, the backward reaction, the decomposition free energy change is negative. That is the logic. Okay, so in this category, you will have silver oxide, lead oxide, barium peroxide, and manganese dioxide. Is this clear? So manganese dioxide also can when you heat. So here, manganese dioxide, when you heat.
Now, could you explain the part where you said what happens that below 500 K?
See, what happens? I am taking mercury and oxygen, correct? I am heating slowly, 50 degrees, correct? 50 degrees, what happens? Your free energy change is negative. 55, 100, 200, up to this, free energy change is negative. Forward reaction will take place. Mercury will react with oxygen to form mercuric oxide. Then lalach badi buri baat hai. You will think rate of reaction will increase. I will bring it to 500. But the moment you bring it to 500, this is 0 plus 10, 20 plus 200. Now what happens is, for the forward reaction, free energy change is positive. Will the reaction remain spontaneous anymore? No. But what about the reverse reaction? For the reverse reaction, the decomposition of mercuric oxide, free energy change becomes negative, and that will become spontaneous. So that story I told you, that if you increase the rate of reaction increases as long as the free energy change remains negative. If at certain temperature for that reaction, the free energy change becomes positive, then immediately what will happen? The backward reaction will take place. The product will decompose and form what you call reactants again. Why? The backward reaction is spontaneous. For the backward reaction, free energy change is negative. Now are you understanding, Priya, what I'm saying?
Yes, sir.
So at 500 Kelvin is a threshold. Less than 500, our old story was working. Heat, more reaction, rate of reaction, very happy. Moment you come to 500, the thermodynamic concepts change. Your free energy changes become positive for forward reaction, formation of oxide. So your free energy changes become negative for the backward reaction. That will happen. This is called a Lingam diagram. Okay, so please take down. So if give scientific reason why mercuric oxide decomposes at temperature greater than 500 Kelvin. So what you will have to say? Below 500, the formation of mercuric oxide free energy change is negative. Beyond 500 Kelvin, the free energy change for backward reaction is negative. So that becomes a spontaneous reaction. It decomposes. So this is the give scientific reason question. Understood? Same is true for silver oxide and lead oxide also. These three are generally what you call MnO2. I did not write that. Mn2, Mn3O4 plus O2. Mn3O4 plus O2. I did complete it because Swayam, you're tired? If we should have ordered a cup of tea for you then. Huh? No, sometimes a little bit of coffee does lot that. Fellow is not come, let him come. Ten more minutes. I'll finish up to properties of oxygen. You understood, Swayam? Up to 500, forward reaction is spontaneous. But immediately what happens after 500? The backward reaction is spontaneous. And that's why we have to eat beyond 500. I saw you looking at it. I was thinking, क्या confusion है? अभी भी नहीं समझा? Backward reaction is, and what is backward reaction? Decompose of the oxide. Now we come to, we finish off this. We come to the large scale method of preparation. There are multiple ways of preparing oxygen. There is no end to it. You can have 50 different methods of preparing oxygen. We'll only concentrate on the important ones where there is some application, where there is some theory, something like that. Is it clear? I mean, you may find in some other books under 10 methods of preparation. No, there is no dearth of that. We look at the large scale manufacture of oxygen. That was very important because you realized that during the COVID second phase, oxygen generators had collapsed, and I think we lost about 40 lakh people totally in the second wave. I mean, the government says 4 lakhs, but then the Americans say 40 lakhs. Americans are better at data collecting. Exactly. Harvard University, not Harvard. Harvard University said it is 40 lakhs. So I believe them. Okay. So what we have in the commercial method, it is not that what happened was that the commercial companies that we have, see, basically all these are what are we doing? this is basically Joule again thermodynamics. If you remember, in your 11th standard states of matter, you had this what you call how to prepare liquid air, liquefaction of air. It was called as not Boyle's process. I forgot the name. Sometimes I'm not able to remember the names of people. That is the problem. Give me a minute. I'll tell you what it is. Linde-Claude process. So you see, Linde-Claude. See, what happens is that what is a commercial method? Simple. Step one, you liquefy air. Don't try to liquefy air in Bombay. It's a poor joke, I know. But then there's too much of less of oxygen. Is this clear? There's more of all kinds of this thing. We can see now what situation we are in. So what normally they do is they have a condensation plant. What does it do? Joule-Thomson effect. What is Joule-Thomson effect? They take air under high pressure and then allow it to come out of a very narrow orifice. That is adiabatic expansion. It is at that point, it's adiabatic expansion. So the gas molecules need energy to go out, work of expansion. Where does it take the energy from? It takes the energy from the gas, internal energy. So temperature of the gas falls. So as you go on doing the repeated compression and expansion, at one point of time, what happens? You come to the critical temperature. What is critical temperature? TC, temperature below which a gas will become a liquid. So when you come to the critical temperature of air, it becomes a liquid. Now, once you get liquid air, then what are you going to do? We are going to do the fractional distillation. When we do fractional distillation, last time also I told you, one by one they start getting separated. So that's the logic. So it's just not distillation. First you have to get the liquid air. For liquid air, it is Linde process or the Claude Linde process. Linde is a company still existing. I mean, I think they are there in India also, because I saw one or two trucks carrying liquid oxygen, liquid nitrogen. It's there. I mean, only thing is we didn't have that many companies to manufacture liquid air so that they can, what do you call, fractionally distill. That is where so the Germans sent, Germans are very good at this. The French, they're very good at these processes. These are called as cryogenic techniques, they're very good at that. So this was a method. So what two-step process? We always in the textbook talk of fractional distillation of air, liquid air. But how do you make liquid air? 11th standard we have taught in states of matter. Claude Linde process. And what is the principle of Claude Linde process? That is the question that we have to answer. It's called Joule-Thomson effect. And what is Joule-Thomson effect? So P block element will encompass certain thermodynamic concepts also. Don't think it's inorganic chemistry, everything is over. No. What is Joule-Thomson effect? In short, I told you, simply you take a gas under high pressure, allow it to come through a small hole to expand into a lower pressure. That is adiabatic expansion. So that's one question. Adiabatic expansion causes cooling. That's another question. Adiabatic expansion causes cooling. So that's the first method. That is by fractional distillation. So you go after the lecture, just go to states of matter and revise through the concept of critical temperature of carbon dioxide. They have discussed that. Andrew isothermal, very, very important. That critical temperature, I am not telling you, because what happens every time if I tell, you see. If you see, you will experience. You have to see and experience. If I tell you ghost look like this, you will not believe me. Experience of ghost, you will understand. Ghost is all these MCQs. It's haunting you. So critical temperature of carbon dioxide, important question. What is Claude Linde process and Linde process? And the principle behind that is Joule-Thomson effect. So by fractional distillation of liquid air, So I told you, how do you get liquid air? You liquefy it. How will you liquefy it? I told you, Joule-Thomson effect. Once you get the liquid, fractionally distill. So fractional distillation will be what? That is, you will get the main constituents are what? You have liquid dinitrogen liquid dinitrogen. Boiling point is 7. Very important from the examiner. Boiling point is 78 Kelvin. Okay. And liquid dioxygen. Liquid dioxygen. Boiling point is 90.2 Kelvin. So what will happen? On distillation, what is going to happen? Liquid dinitrogen distills out, leaving behind what? Liquid dioxygen. Of course, it's not as easy as we are thinking. This will be industrial grade oxygen. Then we'll use charcoal to make it more pure. Huh? So we'll have charcoal in liquid nitrogen temperature to slowly extract it through charcoal way, and there the other gases will get absorbed, or they'll get absorbed, and then we again do stepwise distillation and all that. So a lot of processes there. This is very simplistic view that we are talking. Okay. Then the next is obviously what now we are planning all hydrogen powered trains and cars and all that. So the next method is by electrolysis of acidified water. By electrolysis of acidified water. So electrolysis of acidified water gives you what? Hydrogen is formed at cathode. Hydrogen is formed at cathode. And oxygen is formed at anode in a ratio of, that's very important, in a ratio of 2:1 by volume. 2:1 by volume. So this can be a question on its own. So if you're getting 2 liters of hydrogen, you will get 1 liter of what you call oxygen, and that is used. Now these kind of questions, this concept is used in mole concept to find out what you call amount of oxygen and all that. So there are certain questions. Is it clear? We'll stop here today. Okay, we have just 4 minutes. I don't want to start a new topic. We will continue. So for those who are Wednesday is what? Today is Monday. Wednesday is what date? 24th or 25th? Just check. Because if it is 26th, then 25th. Okay. So next lecture for those who are listening to the live stream will be on Wednesday, 26th Jan at 25th Jan at, we'll make it 6:30 because the other children are facing problem. 6:30 p.m.